All right, so now what we're going to do is we're going to take this equation here, the function we're looking at, and we are going to find the mins, maxes, and saddle points of this function. Now, the very nice thing about this is the steps to doing this is the same as what we did just in Calculus 1, brief calculus, what you're already used to. We're going to take the first derivative, right? Step 1, take the first derivative and set it equal to 0. Why? Well, because any max or any min is going to be found when the derivative is equal to 0. Then we're going to use the second derivatives to look at concavity to determine if it's concave up or concave down. So here we go. So first things first, we need our derivatives. Now, the whole reason we did 15.2 was because we learned how to do partial derivatives. So what we're going to do is the derivative in the x direction. So that would give us what? Negative 3x squared minus 10x minus 7. And then the next term here doesn't have any x's, no x's, no x's, so those are just 0 plus 0 plus 0. So there's our derivative in the x direction. Now we're going to do our derivative in the y direction. So we're going to do the derivative with respect to y. So very similar derivative. That's going to give us 0, 0, 0, 3y squared plus 2y minus 1. Now, the big idea here, when we say do a derivative in the x direction or do a derivative in the y direction, what we're really saying is pretend the other things are constant. So it's the equivalent of taking your graph and rotating it just in one direction. So you're looking at it in just one direction. You're saying, okay, if I'm going to rotate it this way, I'm looking left to right. So I'm only looking for maxes or mins that I see this way. So you see I see one minimum kind of right here, and I see one maximum here. Both of those derivatives are going to come out, or both of those points are going to come out from the setting the x equal to 0, the derivative equal to 0. And then similarly, I'm going to rotate it the other way. So y is changing and x looks like it's straight, just coming straight in and out at me. Whoops, I did it again. I keep touching that side of the screen. But anyway, when I hold it straight, you'll see we'll get a min or a max the other way as well. So here we go. Let's find these values. I take my derivative, I set equal to 0, and now I solve. Now, some of you may have been wondering, why did I make you guys do all that Chapter 1 review stuff? Well, here it is. We need to know how to factor this. We need to know how to solve this when it's set equal to 0. So we can run through factoring techniques and say, okay, let's see, guess and check method, negative 3x, x. That will give me the negative 3x squared. And now I need a 7 and a 1 to make 7. And then, let's see, I need these to add up to be negative. So this is going to be a negative. And so I need that to be a positive and that to be a negative. And that should do it. That should do it. Now, how do we verify that that's the right factoring? Multiply through. Negative 3x times x is negative 3x squared. Negative 3x times 1 is negative 3x. Negative 7 times x is negative 7x. Negative 7 times 1 is negative 7. And that's just the guess and check method. You can use any method you want, but that's just prerequisite material, so I'm not going to spend time right now going over that in this video. All right, so great, we're factored. So now I can say, all right, I now know negative 3x minus 7 equals 0, and I know x plus 1 needs to equal 0. So I have one set of values. When I solve this, I'm going to get x equals, what is, add 7 divided by 3, 7/3. The other one will be at x equals negative 1. All right, so there is my x values for my maxes and mins. When I was looking at my graph, and this jives because we said when we were looking in that direction, we said there would be two different values, one for kind of the top of the hill, the max, and one for the bottom of the hill for the saddle point. And also, let's not forget, we also have this minimum hiding back there. So we're going to see where that pops up, where that comes out. But anyway, so let's minimize this down. Here we go. So that's the x direction. Now let's do the y direction. Set this equal to 0, 3y squared plus 2y minus 1. I'll do the AC method, just for anybody out there who does AC method. 3 times negative 1 is negative 3. What times what makes negative 3 adds together to make positive 2. Well, that sounds like a negative 3 and a positive 1. So therefore, this is going to be 3y squared minus 3y plus y. Nope, try again. Plus 3 minus 1. There we go. So plus 3y minus y minus 1. So now we group. We're going to factor by grouping. So let's pull out a 3y, which is going to give me y plus 1. Over here, pull out a negative 1, which is going to give me a y plus 1. So now I can factor out both of those, the y plus 1s. So that's going to give me y plus 1 times 3y minus 1, and there we go. So now when I set each of these equal to 0, I'm going to get y equals negative 1, and I'm going to get y equals 1/3. Now, here's the next part. Which x and y values go together? Well, the idea here is if I'm getting a value from the f of x direction, this is going to have to get paired up with a y value that came out of the derivative in the y direction. And since there was no substitution or anything that needed to occur, you'll see that in a later problem, I can literally just take this 7/3 and pair it up with this and this value. So therefore, I know I'm going to have critical values. I'm going to have a max or min or something interesting at the value of 7/3, comma, negative 1. Whoops. And I'm going to have another one at 7/3, comma, 1/3. Now, I also have another set of values, though, that are going to come from this one. I'm going to have a pairing at negative 1, negative 1. And I'm going to have another one at negative 1, 1/3. So notice I'm pairing up x with y values, and each value, one has to come from the derivative in the x direction, one has to come from the derivative in the y direction. And this makes sense. We have 4 ordered pairs, and what did we see at the graph? We saw 4 critical values. We're going to have a saddle point, a maximum, another saddle point, and then around on the back side, a minimum. So we have all 4 things. It's looking good. So now this is 3-dimension. This is just the x and the y. How do I get my z's? How do I get my output values? Well, here we go. Take your x and your y and sub them back into the original equation, just like we did with the original derivative problems, right? Once we got our x value, we had to use those to get the y. Now that we're in 3D, we have to use our x and our y's, our 2 independent variables, to get our dependent variable. So I'm going to go ahead and sub those in. I'll pause the video and I will be back. Quick little fix. My apologies, it's going too fast. When you're solving this, that should have been negative 7/3, right? So therefore, that would just change that to negative 7/3, that to negative 7/3. Okay, now I'm going to get the values. Okay, so now that I've corrected it and put in negative 7/3, there we go. Our answer should be 76/27, 44/27, 4, and 76/27. And kind of thinking about our graph, this makes a bit of sense. These two have the same z value, right? These have the same z value. And when you looked at the graph, didn't we have 2 things that had the same z value? Here we go. If I zoom out just a tiny bit again, let's see here, and let me do one step out. There we go. When you look at your 2 saddle points, do you see they're kind of at the same height right there and right there? Then we're going to have one higher value for the max and one lower value for the minimum. So when you look here, these I'm predicting are going to be the things I circled here in the green is going to be the saddles. 4 is the highest value, so I'm guessing this is going to be the max, and I'm guessing this is going to be the min. Let's verify this, though, using second derivatives. Okay, so second derivatives. Here we go. Let's actually figure these things out. All right, second derivatives. All right, so stealing my f of x from right up above, taking my first partial derivative of f with respect to x, I'm going to do the second derivative, second derivative with respect to x. So that would result in what? Negative 6x minus 10. Okay? And then I need the second derivative with respect to y. That would be this equation right here. So this would result in what? 6y plus 2. Now, we need to use these second derivatives for each of these points off to the side. So for me to figure out, we're going to have to do each critical point individually. So let's call this one A, B, C, and D. Okay, so starting with A. In these equations where wherever there's an x, I'm going to replace it with negative 7/3, and everywhere there's a y, I'm going to replace it with negative 1. So here we go, 4, negative 7/3, negative 1. Here we go. Let's see, the second derivative would be what? Negative 6 times negative 7/3 minus 10. Now, the simplification on this isn't too bad. That divides with that, leave me with negative 2. Negative 2 times 7, which would be positive 14. 14 minus 10, which is 4. Now, to be honest, I really don't care about the number. All I care about is that it is positive, which means in the x direction, we are concave up. Now let's check the y direction. In the y direction, my second derivative is, I'm going to use a negative 1 for all my y's, so that'd be 6 times negative 1 plus 2. So that's going to be negative 6 plus 2, so that's negative 4. Once again, don't care about the actual value. All I care about is that it is negative, which means I am concave down. Okay, so positive in one direction, negative in the other. That's the definition of a saddle point. So therefore, I know at the value of negative 7, 3, negative 1, and 76/27, this is a saddle point. Let's do it again for B. All right, now the good news. I've already done it for the negative 7/3, and this, since my f of x, my second derivative with respect to x, doesn't have any y's in it, this ain't changing. It's still 4. So now all I got to worry about, so I'm going to kind of just do a little revamp. I'm going to make this 1/3, right? So now this second derivative, I still substitute the negative 7/3. That didn't change, but this is going to change. So we're going to redo this. Okay. So now everywhere I have a y, I'm going to replace it with a 1/3. And again, I don't care about the values. A positive times a positive makes a positive. A positive plus a positive makes a positive. This thing's a positive. But if you want to actually get the values, 6 divided by 3 is 2. 2 plus 2 makes 4. Therefore, this is positive. It is concave up. Up in one direction, up in the other direction. That means this thing is a minimum. So right here, this is our min. Now, while I have this on the page, I already have 1/3 substituted in. Let's jump to D. Let's go to this point to check, because I don't need the negative 7/3 anymore. I've done all my versions of that. So let's get rid of this. Now let's test the point of negative 1/3. Let's see what that is. So when I substitute in, when I substitute in for f of x, I substitute negative 1. Negative 6 times negative 1 makes positive 6. 6 minus 10 makes negative 4. So you can see we are negative. So I have a negative in one direction, concave down, positive in the other direction, concave up, one of each. This is a saddle point. As we predicted, these two are saddles. Okay, last but not least, let's check the point C. Let's check the -1, -1. There we go. I already have the -1 substituted in for my second derivative with respect to x. So let's go to the second derivative with respect to y. Substitute in -1. So 6 times -1 is -6. -6 plus 2 is -4. This is negative. So therefore, it is concave down, which means we have a max. Not because I have a negative second derivative in one direction, but I have it in both directions. So therefore, I have a maximum. So this last piece here, this is a max. So we have 4 critical values. We have identified all of them. We know that they are mins, maxes, and saddles. You have your x, your y, and your z values. We are done. All right. This was how we do a problem that doesn't have interaction. Now, if the problem did have interaction, we're going to do something very, very similar. We're just going to use this equation here. And you'll notice it still uses the second derivative with respect to x and the second derivative with respect to y. There's just an interaction derivative here. That's just going to, it actually doesn't change how we read our answers. It's just, it gives us an added opportunity to verify what we're doing. So on the next problem, we're just going to talk about, in the next video, we're going to talk about this equation. How do we use it? And then we're going to do a problem that has interaction. All right, we'll see you then.